Professor Yoo is a long-term member of our ARM Academic Access programme and has been involved in multiple research projects, including using EEG, so brain signals, to detect seizures and air channel ultrasound to replace drone vision. So Jerald is a professor of electrical and computer engineering at Seoul National University. He received his PhD degree in electrical engineering from KAIST Korea in 2010. He's pioneered research on body area network transceivers for communication and powering a wearable body sensor network for continuous health monitoring systems. So I'm very happy today to introduce Jerald's lecture, and at the end we'll have time for questions. So we'll be recording our session today. And for questions at the end, we'll be taking these in the traditional way of a lecture. So without further ado, I shall introduce Jerald, and looking forward very much to hearing his lecture.
Yep, thank you very much for the excellent introduction. My name is Jerald Yoo from Seoul National, as Becky said. So today I'll be talking about body area network of my series of research. This is one of the research that I also emphasize very much on to connect with the healthcare as well as communications around the body. So this is the outline. I do not use the RF just like the other people are doing when you're connecting the sensors, providing connectivity to the sensors, but rather I'm using the human body itself as the communication and powering medium, which is unconventional. So that's why I had to start off with the channeling of the human body, which I'll be talking about in a while. And normally this is a 4-hour lecture, so I just trimmed that down to 45 minutes, 50 minutes. So I'll probably skip the interface part, but I'll go ahead with the transceiver for communication and then move on to the powering. But before I start, let me also talk about why do we need to have a body area network per se. And one of the examples of the application in body area network is the healthcare, and also as well as mobile healthcare, that's why I call it. And the reason we need it is because so far we have been talking about having diseases and then reacting to that disease then when the symptom comes up. But right now we are having the paradigm shift here where we need to intervene before the health gets deteriorated. So that means that if you have a proactive healthcare, in order to do that, we need to have a continuous monitoring over the body, which is easier being said than done. All right, there are many, many problems. So sensing is one of them. Collecting the data along the sensors is another thing. And then how to communicate to collect the data into a central medium is another one problem. So to enable that, we need to have the wearable healthcare with the body area network. In short, we call it BAN. So what's so special about body area network? Well, if you look at this range over here in the right, down over here, the body area network typically covers up to 2 meters in diameter or radius. And that's because human beings typically less than 2 meters in height. And as you can see, the coverage is small, but yet the data rate as well as the reliability becomes very, very important. And that's where it differs from the rest of the RF transceivers. And let me talk about that in terms of the power consumption as well as the data rate. So if you look at the power consumption on the x-axis, we have some of the Wi-Fi or Bluetooth low energy, so to speak. Zigbee, we don't use that much these days, but there's standard there. And if you look at in the power consumption point of view, to enable the continuous monitoring, we actually need to have really low power. So Bluetooth low energy, for example, which typically lies in the tens of milliwatt, if not around 1 to 10 milliwatt, is low power enough for RF. But for the body area, that's not low power enough. And also, if you look at the data rate, we are targeting around 1 Mbps or up to tens of Mbps. So I would say what is missing spot right now as of today is the blue star there, which I'm targeting around tens of Mbps and probably well below sub-milliwatt. Another thing that I also want to emphasize is that my research is actually related to integrated circuit design, and many circuit designers actually focus on 5-layer physical layer energy efficiency, which is in other words, energy per bit. Joules per bit, which is very important, but that's not only thing that we should focus on. Actually, there's also something called MAC layer, we all know, and also the data link layer, as well as network layer and application layer. And when you mix some sensors around, which are different in the aspect or characteristics, for example, if you have like let's say, for example, continuous type of sensors such as ECG, EEG, which requires you to monitor 24/7. And then you also have the sensor which only requires like 10 to 20 times per day sensing, such as the blood pressure or glucose, for example. Probably accessing the medium is something that we also need to focus on. Otherwise, if you just use the conventional contention-based access, for example, a lot of times you don't actually need to sense the channel for the EEG type, glucose or EEG type sensors, because the spontaneous sensors are only sensing from time to time, but you still need to waste energy in sensing and resolving that MAC access. So this is another example where not only the PHY layer efficiency, but we also need to look into the MAC and network layer. It's also becoming more serious if you have the stimulating type of sensors, for example, like ICG, for example, or electroacupuncture coming into the domain. Now, that being said, the easiest way to compose the body area network, of course, if you can think of, is using the conventional RF, such as you have the RF sensors, using the Bluetooth low energy, for example, which has a good news about it is that it's very convenient. And practically, there's no limit of how many sensors you can connect into, because you're not going to wear probably 300 sensors around the body. So practically, there's no limitation on number of sensors. But one problem we can say is that we by default think that we are going to use the batteries, which I'll be talking coming back with that. But think about having lithium battery when you're taking shower. Probably I'm not going to use them. There'll be some concerns with it. And more importantly, there are some potential interferences, which not many people are talking about it. So what do I mean? So there are some problems with the RF on body. RF in general, we don't have any issues. But when you're bringing the RF to the body area, there's a big issue. Because from 1 gigahertz around 10 gigahertz, I would say 1 gigahertz to 5 gigahertz, the human body actually absorbs a lot of energy. And this is a known fact, right? And unfortunately, many standards that the wireless standard we are using lies in that bandwidth. And this actually comes to my own experience. When I was a graduate student, I was doing the tape out. I was very stressed out. I remember that 2005, and that's around the time when this Bluetooth headset came into the market. So I was stressed out, so I went out for a walk. I remember it was around 11 p.m. And I had the music player inside my pocket, and then this Bluetooth headset I was wearing. And then I went outside or walking around, and so all of a sudden the music stopped, right? And inside the room, there was no issue. And I noticed that when I'm stationary like this, then I don't really hear anything. And interestingly, when I started moving around, intermittently, the music was coming back and forth, coming back, cut, and coming back. And so I was wondering what's going on there. At that time, because I was preparing the tape out, I didn't have time to look into it. But later on, I found that this is because when I move around, there's a reflection from my hand and my limbs, which enable this RF from communicating. So there was no line of sight. I didn't know that, but at that time, the player and the Bluetooth receiver didn't have line of sight. And human body, which is myself, was absorbing a lot of energy. Unfortunately, that's where the blockage happened. So human body absorbs RF energy, which is not good for healthcare sensors. It means that you can still communicate, but the TX power has to be increased significantly, which drains the battery pretty soon. And this is actually a well-known fact for those are on RF. By having the antenna just in proximity of the body, you don't even have to attach it, but if the antenna is in the proximity of the body, then the radiation pattern is distorted significantly, which requires you to actually think over how well I have to shoot over, how much power I need, which is not in favor of you. So this is why I say RF in general is okay, but when you're talking about RF on body, that's a problem. So that's where I came into thinking about using the human body as the communication medium instead of using it as blockage. And that's where we call it as body coupled communication, as the name speaks itself. Now the human body becomes the medium, not the blockage. So if the human body is blocking the energy, let's just use it for coupling. And there are largely three ways of doing that. One is the magnetic coupling, the second is the galvanic, and the third is the capacitive coupling. Of this, there have own pros and cons. The magnetic coupling is fairly efficient. You just need one limitation it has is that you need to have the limbs I mean, there's a coil which generates the magnetic flux. So you need to have a limited form factor. It has to have some round surrounding your body. So if you're using, for example, smartwatch, which you already have the surrounding, then this is perfect fit, right? Now the second type is the galvanic current, galvanic coupling, where you have the electrode on both on the TX, double electrode, signal and ground, and then the RX, which also the signal and ground, which has a good, I would say, robustness against the human body movement, but at the same time, the path loss is quite significant. So it has also its own domain of application to look into. The third type, which primarily I focus on, is the capacitive coupling. It looks fairly similar to the galvanic one, but if you look carefully, there's only one electrode on the TX, one electrode on the RX. Then the return path is formed by the capacitive coupling of the ground electrode to the earth ground, which means, on one sense, you can cover the entire body, which is good news compared to the galvanic coupling. But the bad news is, because you're relying on the capacitive coupling to the earth ground, as you move around, the signal quality will be varying significantly. I call it ground effect. All right, so in a nutshell, what the body coupled communication is that we have the TX and RX with the single electrode. You're going to shoot the energy from TX to the RX using the human body as a coupling medium. And as I will emphasize what I said, if you're talking about the RF in general, probably that'll be most efficient, except when you're talking about the RF on the body. If you compare with the body coupled communication, then the BCC is much better. This is the path loss on the y-axis. So if you compare with the RF on body, the BCC wins in terms of the path loss by around 20 to 40 dB. All right. So with that said, I normally talk about the body channel followed by the interface and then transceiver and powering. Powering a network, but I'll skip the interface to the interest of time. I'll just talk about the transceiver and then the powering network. So that said, as I said, because this is not something, it's fairly new in the field, so I had to start off with measuring the body channel. What's the path loss against the distance, against the posture, and many factors, including movement even. And then we also had to jump around and see if there's a variation in the path loss. And there is. So this is something we have to also look into. Now, you may be thinking, what's the big deal? Just use the RF generators and then measure it with the spectrum analyzer in the other end. But unfortunately, what happens in that case is, if you remember, these RF generators are connected to the power outlet, which means a firm connection to the ground. And then a spectrum analyzer also has a firm connection to the ground. So if you measure it with the wall-mounted RF generators, the wall-mounted spectrum analyzer, the path loss that you measured is fairly optimistic. In the real wearables, there's no ground connection to earth ground, as you may imagine, right? The watch doesn't have the earth connection, right? Which means the path loss will be much more significant. So that's why we had to use balloon, for example, here to separate the grounds, and both in the TX and the RX side. We also, I'll talk about this. We also had to, of course, de-embed the coupling between the cables and the body, as well as the interface. All of these has to be de-embedded. But good news is that once you measure it with that, we found that the path loss characteristic of the human body looks like a bandpass filter. So between around 40 megahertz to around 100 megahertz. So that's why we decided to use that as a center frequency, around 40 megahertz to 120 megahertz, where the path loss is the minimum. The good news is that if you fix everything, the same subject, same subject, same day, same office, same location, same posture, then the path loss remains almost constant, let's say within around 2.5 dB variation. But the bad news is, once you move around, which wearables will be always moving around, and if you have different subject, or even if you're on the ground floor versus in the 10th floor, then the path loss characteristics changes abruptly. So there may be around even 20 to 40 dB variations, which is not good. So that's why the transceiver has to adapt to these type of variations. And interestingly, different subjects also have different path loss characteristics. So for example, if you look at this particular subject, probably I don't want to use 65 megahertz for this red line subject here, because that for some reason, at that 65 megahertz, I have the dip, which means that the path loss is really, really big there. But that's not always the case. If you look at this person over here, that person doesn't have that dip, so it's no problem using 65 megahertz for that person. So this implies that we have to adapt to each person's characteristic on the path loss as well. Just to summarize, on the channel, the BCC, which is body coupled communication, shows strength over RF on body. Again, I emphasize I'm not competing with the RF in general. I'm talking about RF on body. Compared with that, BCC is much better in terms of path loss. And capacitive coupling is chosen because of the full coverage in the body. And we found that around 40 megahertz to 100 megahertz should be the best bandwidth to use in terms of the path loss. But at the same time, I have to deal with the non-identities such as the varying Brown effect or varying skin electrode impedance, multipath interference issues, for example. So that said, let's move on to the transceiver. Now I know that we have some varying conditions. We also have in-band interferences and unknown channel across different people. And we might be thinking, let's use the OFDM because OFDM is just perfect for this type of situation for unknown and varying fading channel, for example. But it's very power hungry, right? So this is why we had to come up with some other ideas as well. And let me give an example of the BCC. This is not the only solution to use it. I remember that we had the BCC transceiver first presented in ISSC 2006. And then we had a nice demo set and it was working perfectly in the lab. And we went to San Francisco, it didn't work. So at that time, we didn't know what the problem was. And it turns out that the walkie-talkie that the security guards are using, which is professional grade walkie-talkies, are so strong. And that time, the PHY transceiver was using the CDMA, code division multiplex spread spectrum. But the walkie-talkie was so strong, even after spreading the spectrum, it was still higher than the signal component. So it didn't work that way. So these were good lessons learned. So then we chose, okay, in that case, we should have the known in priori interference sources like this and just skip it. This is the active frequency hopping that can be used. But even with that, the unknown or varying channel condition cannot be overcome. So in this case, we can use the OFDM. But the problem with the OFDM is as follows. Because of the huge variance on the peak power to average power, the power amplifier has to have large linearity, over the wideband. And that actually gives a pretty, not wideband, but over a lot of power on the x-axis, which requires power consuming block on the power amplifier as well as DAC. So that's because that in the OFDM, there's a peak power to average power big difference. And we found that you can just overcome that by eliminating the power amplifier and DAC as a whole. So we are not using the orthogonality anymore, but you do the baseband OFDM coding and then go through, for example, a BPSK, for example. Then what you're basically doing is you're expanding the bandwidth. So you're eliminating all the need for the power amplifiers and the DACs, which saves a significant amount of power. But at the same time, what you're doing is you're expanding more bandwidth to deal with. And if you're talking about more bandwidth occupation in RF, that's something that people will not buy because every hertz is $1 in RF. But whereas in the body coupled communication, your signaling is done through your body channel. So this is why you can pay off some more bandwidth in terms of bandwidth to realize more stable communication. So if you compare with the conventional analog OFDM versus the proposed, we call it pseudo OFDM, with the baseband coding, you're expanding and you're occupying more bandwidth. We found that you actually gain a lot in terms of the BER performance. But that's one way to go, actually. As I said, you can have the adaptive frequency hopping to avoid the known priori interference sources, and then use the OFDM, hybrid OFDM. And if the measurement shows around 70% reduction in the BER, improvement in the BER performance compared to the hybrid OFDM applied versus not. And the measurement was done at around 120 centimeters. You can communicate up to 180 centimeters, no issues. right? So there are some transceivers that we designed. Okay, if you look at the power consumption, remember in the beginning I said we are targeting around sub-milliwatt. That version is still not, the version that we are proposing is still not that yet, but the more recent version is. And we're talking about the data rate of about 2 megabits per second, which was more than sufficient for most of the healthcare applications. Just to summarize on the body channel, body area network BCC transceivers, we talk about why do we need to have the body coupled communication in the first place? Is because RF on body is not that efficient because the human body is absorbing a lot of energy. So that's why we came up with the idea to use the body as a coupling medium to communicate. But by doing so, we have to deal with some interferences as well as the varying environment and return path conditions, which can be overcome, for example, with the hybrid OFDM. And for the interference sources, you can avoid by having the adaptive frequency hopping. But there are many, many things to overcome per se. But by doing so, as I said, compared with the RF on body, this will be a nice way to extend the battery life. And why not use the OFDM just? Because by using the OFDM, then you're actually consuming a lot of energy from power amplifier and then DAC. And let's not forget what was the reason we are going for body coupled communication was to save power, right? Because compared to RF on body, the path loss is much less, then potentially you can save power. But by applying the OFDM, you're losing all that gain that you got of power consumption savings. So that's why we decided to go for hybrid OFDM, for example. So with that, let me go ahead with the body area network for powering. If you recall one of the earlier slides, I said that when you're composing a sensor, like the wearable sensor, by default, we are thinking we're going to use battery. And this is what many people, and this is the same mistake I made, was working perfectly fine. But when we applied, for example, another research that I do is the seizure detection. And until I actually applied this to the patient, I didn't know about this problem. So once the battery comes in, all sorts of problem happens. I'll come back to that what it means. For example, the battery is the bulkiest part in the wearable, most of the wearables. And because of that, in the patch with the wearable, you're having some inertia from the battery, which makes the sensor interface circuit with much bigger motion artifact than before. And this is a big problem, for example. If you can actually trim down the volume of the battery, or if you can actually remove it as a whole, that's the best story. So that all sorts of, like say, wearable sensors, they are all using batteries by default. But before I move forward with the topic, let me ask you in this room, how many wearables are you carrying? So for example, I have the smartwatch, I have the AirPod, I have 2. I will consider the mobile phone as wearable. So I have 3. How many of you are carrying 2 wearables? Okay, very good. 3. All right, 4, 5 plus. Okay, believe me, I go worldwide and do this presentation. I have seen one person with 5 wearables, but most of them are 3 or less. And I was thinking about it, why is the case, right? And I think that one of the reasons is because imagine you have 10 different wearables and you have to charge this every night. Oh my God, I have to charge like a mobile phone, then I have the AirPod, I have this ECG sensor, and oh my God, I cannot take care of 10 different wearables to begin with, not to say 20 wearables, forget it. And we use all wearables, smartwatches, earphones, and hearing aids. But if you look at the contemporary wearables, frequently I'll be talking about this, but the future features are left out due to inadequate power. In other words, if you had sufficient power or energy source, you can put more features in it. But unfortunately, due to the lack of power, you can't do that. Second is to pressure to make the wearable smaller. For those who may already know, if you look at the wearables like a smartwatch here, the most volume taking piece of device is actually battery. And this is most of the time the same for most of the wearables. And more importantly, user stress of constantly charging wearables is another thing. Like 10 different wearables charging is one thing, but bigger problem is, okay, I have my smartphone 59%, ECG sensor is running out with 30%. Oh my God, AirPod is now 70%. Think about it, this is really stressful, right? So batteries are bulky, insufficient, and incurs charging overhead, and probably we may, alleviate this by having power delivery or harvesting, right? If you can get away from it. But let me give you one example of the features left out that I mentioned. I hope you don't have to use it, but in the hearing aid, there are largely two types. One is the behind the ear type, and the other one is the in-canal. The in-canal type, and for obvious reason, everyone wants in-canal type, because I don't want to show that I'm wearing the hearing aid. But because of the volume, which is very small, the in-canal type is very small, the batteries are very small as well. And because of that, the advanced features that the behind the ear type has is not integrated. So for example, the pioneering hearing aid, or let's say adaptive gain control and these or noise reduction, these schemes are more often left out in canal type. So it's a battery problem. All of these are actually ultimately interlinked with the battery. They're insufficient and large and inconvenient for charging. So then, okay, I know that it's a battery problem, I understand it. Then how about we go for energy harvesting? The harvesters are fairly efficient these days, remember? But there's one issue, all right? Think about the PV, for example. It requires exposure to light. And let's say if you want to powering up the ECG sensor in your chest, which is covered with the clothing, then there's a location, I call it location mismatch. The PVs are operating ideally when it's exposure to body, to air, such as the head or limbs, which may not be aligned with where you need the energy from. The same problem with the thermoelectrics or piezo or triboelectrics harvesters, which is the same. So as I said, this is what I call as a location mismatch. The harvester themselves are fairly efficient, but often they are unable to cover the full body area. So then, okay, I understand that. Then why don't we use the power like transfer from one point to the other, right? You can harvest the energy from where it's most efficient, like PVs in the limbs or in the head, and then transfer the power using wireless power transfer, right? That's what you can do, right? You can use the wireless power transfer. But you heard me, right? You heard me about the body coupled communication. The problem with the RF on body is that the human body is absorbing a lot of energy. And same problem happens here. So if you have the distance from the TX to the RX, between TX and RX, and you have the path gain here, by just having the antenna near the body area, you get around 20 dB path loss. I already mentioned this to you. And then that's when you have the line of sight, meaning that, okay, the TX is here, RX is here, you have a line of sight, you still have around 20 dB path loss because of the human body interacting with the antenna. Now, things get even worse if there's no line of sight. So for example, if the TX is in the chest, RX is in the back, and you are outside the room where there's no reflection, then you get additional like 30 dB path loss. So it's, once again, just like in the communication case, this makes it quite inefficient for using the RF-based wireless power transfer. It means that you can do it, affirmative, you can do it, but with a lot of significant reduction in the energy, significant power loss during this transmission from one end to the other. And if that's the case, I already mentioned to you, this was the motivation for me to go from RF communication to the body coupled communication. And at one point we thought, if the communication is possible, why not powering? And that's exactly what we're doing. By using the human body as a coupling medium of power transfer, we can actually boost up the path loss. Boost up the efficiency by around 20 to 50, even 50 dB. There's no line of sight. So compared to the RF on body, this is much more efficient. Of course, the downside is because you're using human body as communication medium, you must have in contact with the body. Both the TX and RX must be in contact with the body. But if this is a wearable, which is in contact with the body anyway, probably that's not a big problem. And interestingly, you don't recognize it, but as you're sitting in this boardroom, you don't recognize it, but significant amount of 50 hertz from the power line is coupling to your body already. All right, we have measured it, and believe me, it does. And right now we're not using it, right? But it actually goes to your body and goes to the earth ground. And using the same receiver, you can actually harvest the energy from the 50 hertz. In Korea, it's 60 hertz sources. You might be asking, is it safe? That's the first question you might be asking. But just to rest be assured, the power level we are harvesting or transmitting is about the same level as you are actually harvesting. And you're not harvesting, but you're coupling to the power line as of now. So if you are concerned about this technology, you should be more concerned about the coupling that you cannot avoid these days. Okay, and there are some, okay, I should skip this part. This transceiver. So how do you actually do that? It's basically the same technology I've been emphasizing on the body area network transceiver. So you have the power transmitter, which is transmitting the power from the one end. And you will need to have the detuned impedance booster because in the typical RF communication, you need to have a high Q to have a efficient communication. But due to the variation on the environment, due to the posture and many things, you need to have a wide band capturing. So we intentionally detune the booster. So they have a wider capturing range. And then you need to have the rectifier, which is tuned for low threshold. And then while suppressing the leakage and then getting the low threshold, we have the adaptation rectifier, depending on the input levels. And because there's a big difference between the harvesting versus transfer in terms of power level, we need to have the dual mode buck boost converter at the same time. And we are utilizing the capacitive return path, as I said, in the communication as well. And that's how it behaves. So let me give you one video as an example here. So here I have the transmitter, power transmitter, with the one single electrode. And then the receiver also has the calculator, the battery removed, and it also has the one electrode on the RX. So you don't, you intentionally avoid having the explicit closed loop or another range of safety. But nevertheless, now I have the transceiver, which is shooting the power from one end. And as you can see, if I don't touch it, there's no calculator powering up. But my goal is to power up the calculator through the human body couple. And as you can see, it's operating as intended. And we tested up to around 20 sensors, 20 calculators we can power up with the same TX. So it's actually using the same method that the body coupled communication has been using. And I brought the demo set here so you can try yourself. Believe me, it's very safe. Just to conclude, we are in the era of, let's say, proactive healthcare, and that requires not only the good sensing, but also good communication and network formation as well. And for that, we would like to use body-coupled communication because the RF on body is very inefficient with the extra path loss that you get. So to enable that, we can use the capacitive BCC or body-coupled communication. But at the same time, by using that, you need to overcome some non-idealities, such as the varying skin electrode impedance or the varying ground conditions, as well as the interferences that you have to deal with. In the future directions, I showed you how to use the body-coupled power transfer to power up the wearables, because this is also related to the convenience factor. I mentioned at the beginning, it's not only about the file layer efficiency, but you also have to think about the MAC layer, as well as the network and application. And in terms of application layer, convenience is very, very important. However good technology you may have, if it's very difficult to use or it's inconvenient to use, people will not use it. And that's where I want to tackle. And BCP enables you to doing so. And I didn't mention it today, but you can also do the concurrent BCC and BCP for true body network using the same electrode, right? Same electrode, you can do the power transfer and then communication, which is not easy, of course, but you can do that with the circuit features to overcome. So by doing so, what you're doing is now you have the base station, for example, a smartphone in your pocket, which is providing power to the rest of the sensors. And then the sensors are communicating back to the smartphone using the BCC at the same time. So you can do the BCP and BCC at once for advanced or more convenient sensors. All right, so that's it for the presentation part. If you have any questions, I'll be happy to answer. And just for the sake of fun, as I mentioned, you can probably try this. Okay, let me see. There we go. You can see that this is the TX, this is the RX. If you touch it, very fancy. You can circulate and then test it yourself.